Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Rusmania. I will explain about Van der Waals equation.
How can the ideal gas law be modified to yield an equation that will represent the experimental that more accelerate? We begin by correcting an obvious defect in the ideal gas law, namely the prediction that under any finite pressure, the volume of the gas is zero, the absolute zero of temperature. P equal RT divided P. Uncalling real gas, liquid, and ultimate solid. After liquefaction, the volume does not change very much. We can arrange the new equation so that it predicts a finite positive volume for the gas at 0 Kelvin by add a positive constant B to the ideal gas volume. V equal B plus RT divided P. According to equation above, the molar volume at 0 Kelvin is B, and we expect that B will be roughly comparable with the molar volume of the liquid or solid. Equation above also predict that as the pressure becomes infinite, the molar volume approaches the limit value B. This prediction is more in accord with experience than the prediction of the ideal gas law, that the molar volume approaches zero at very high pressure. Now it would be interesting to see how well equation above predict the garbage. Since by definition Z equal PP divided RT. Multiplication of equation above by P divided RT yield Z equal 1 plus BP divided RT. Since equation above requires Z to be a linear function of pressure with a positive slope, B divided RT is can possible with the carbon for nitrogen, which start from the origin with a negative slope. However, equation above can represent the behavior of hydrogen. The dashed line is a plot of equation above when at the origin to the cover for hydrogen. In the low pressure region, the dashed line represents the data very well. We can conclude from equation above that the assumption that the molecule of a gas have finite size is sufficient to explain value of the greater than unit. Apparently, the size effect is the domination one in producing different from ideality in hydrogen at 0 Celsius. It's also clear that some other effect must produce the definition from ideality in gas, such as nitrogen and methane. Since the size effect can explain their behavior in the low pressure ring, this other effect must now be solved. We have already noted that the worst offenders in the matter of having value of Z less than unity are methane and carbon dioxide, which are easily liquid. Thus, we begin to suspect a connection between AC of liquefaction and the compressibility factor. And to ask why a gas liquid. First of all, energy, the heat of vaporization, must be supplied to take a molecule out of the liquid and put it into the vapor. This energy bursts in the liquid. The force of attraction is strong if the molecules are close together. As they are in a liquid and very weak. If the molecules are far apart, as they are in a gas, the problem is to find an appropriate way of modifying the gas equation to take account of the effect of this weak attractive force. The pressure exerted by a gas on the walls of a container H in an outward direction. Attractive force between the molecules tend to pull them together, thus diminishing the outward thrust against the wall and reducing the pressure below. That exerted by the ideal gas. This reduction in pressure should be proportional to the force of attraction between the molecules of a gas. Consider two small volume elements V1 and V2 in a container of gas. Suppose that each volume element contains one molecule and that the attractive force the two volume element is some small value f. If another molecule is added to V2, keep one molecule in V1. The force acting between the two elements should be 2F. Addition of a third molecule to V2 should increase the force to 3F, and so on. The force at attraction between the volume elements is therefore proportional to C2. The concentration of molecule in V2. If at any point in the argument the number of molecules in V2 is kept constant and molecules are at 2V1, then the force should double and triple, etc. The force is therefore proportional to C1, the concentration of molecule in V1. Thus, the force acting between the two elements can be written as force C1 C2. Since the concentration in a gas is everywhere the same, C1 equals C2 equals C, and so force C ring 2, but C equal N divided P equal 1 divided P. Consequently, for 1 divided V rank 2. We rewrite equation in the form P equal RT divided V minus B because of the attractive force between the molecule. The pressure is less than that given by equation above by an amount proportional to 1 divided P rank 2. So a term is subtracted from the right hand side to yield P equal RT divided P minus B minus A divided V rank 2, where A is a positive constant roughly proportional to the energy of vaporization of the liquid. Two things should be noted about the introduction of the A divided V rank 2 term. First, the figure of volume element in a gas. The table of Van der Waals constant for gas He 0.00345, 23.4, H2 0.0247, 26.6, O2 0.138, 31.8, CO2 0.366, 42.9, H2O 0.580, 31.9, Hg 0.820, 17.0. Acting on any volume element in the interior of the gas balance out to 0. Only those elements of volume near the wall of the container experience an unbalance force that tends to pull them toward the center. Those The effect of the attractive force is felt only at the walls of the vessel. Second, the derivation assumes an effective range of action of the attractive force of the order of centimeters. In fact, the range of this force is of the order of nanometers. In chapter 26, we do the derivation without this assumption and obtain the same result.